Hello and welcome to today's chapter. Sorry about the sound. This is a continuation of what we did in the previous chapter, chapter 3. And we're going to look at how we get information from very distant objects. And first of all, we'll look through the electromagnetic spectrum, discuss that in a little more detail than we did in the previous chapter, talk about telescopes, a little bit of history here, and how they've changed over the years. We'll talk about a very important instrument known as the spectrograph. Many times people have a misconception about astronomy that the most important information that we get from distant objects are images. And certainly the Hubble images have shown us beautiful things out there. But actually we get a lot more information sometimes from the spectra of these objects. As we talked about previously, the spectra tells us about the temperature, tells us about the composition, and even about the speed of the object. So these spectrographs are very important in helping find that information. And finally, we'll talk about space probes. Now, we can't use space probes beyond our solar system, but all of the planets have been visited at least once by at least one space probe. And there are even space probes on their way to some of the dwarf planets, such as Ceres and Pluto. So in any case, let's start with the electromagnetic spectrum. Electromagnetic waves, as their name implies, are oscillations of electrical and magnetic fields. And, the farthest human beings have traveled in terms of outside the Earth is the moon. That's as far as we've gone. And the moon is our closest celestial neighbor. So, as far as being able to visit place and take samples back, we're very limited, in terms of astronomy. In geology, we can travel to different parts of the world, take samples, bring them back to the lab, analyze them. Same thing is true with archaeology and anthropology. We just need to, travel different places in order to, be able to obtain different samples. But, in astronomy, you really, as far as our solar system, maybe you can have a space probe travel to it, and it takes years to arrive at some of these planets. But beyond our solar system, and that's where most of astronomy, studies, you can't really go all that far. So we have to take the information that comes to us. Of course, we know that sound waves don't travel through space, so we can't rely on one of our senses, and that's hearing. The only thing that we can really do in terms of getting information, or the primary thing that we can do, is look at electromagnetic radiation. Electromagnetic waves are, again, electric and magnetic fields that are oscillating through space. And light is a very good example of an electromagnetic wave. And unlike sound waves that need a medium to propagate through, the medium for electromagnetic waves is space itself. Now, not only are the waves, electromagnetic radiation also is composed of individual particles known as photons. These little particles are packets of energy, if you will. I guess a better way to view it is, instead of just a solid sphere like we see in this image, is a little tiny wave, if you will, a little compact wave pulse is what these photons could be viewed as. In they can act as individual photons, or they can act on a large scale and combine with one another. Now, the electromagnetic spectrum consists of 7 parts. The longest wavelength are the radio waves, and they have the longest wavelength, the lowest frequency, the least amount of energy per photon. Then comes the microwaves, whereas the radio waves might have wavelengths in the kilometer length, the meter length. Microwaves are typically closer to the centimeter length. Infrared, anywhere from wavelengths in the millimeters to the micrometers. Visible light, what we can see, is somewhere around the half micron range. Then we start getting to really small wavelengths. This type of radiation is also ionizing, so it's dangerous to us. Ultraviolet light, X-ray, and finally the The shortest wavelength, the highest frequency of all the electromagnetic waves, the highest energy per photon, and the most dangerous are the gamma rays. So electromagnetic waves can be categorized according to their wavelength or their frequency. Wavelength and frequency are inversely related when we're talking about these waves. And wavelength is a distance that one oscillation takes to repeat itself. Frequency is how many oscillations we get in a unit period of time. Usually if we're measuring it in hertz, it's how many oscillations are happening per second. And again, because light is composed of individual particles, individual photons, the frequency of the light actually determines how much energy it has. So radio waves have the longest wavelength. They're going to have the lowest frequency. Therefore, radio waves barely have any energy at all in their photons. Thus, radio waves have a more wave-like characteristic to it because their individual particles don't carry very much energy and don't carry very much momentum. It's the combined effect of the total wave, which is oftentimes important when we're dealing with the interaction that radio waves make. As we get to shorter wavelengths, the photon energies become larger and larger. And eventually, once you get up to the visible part of the spectrum, the photons have enough energy to actually interact with matter on a nearly individual scale. Yeah, microwaves can actually cause things like a nuclei to flip, individual molecules to rotate, but it's really not until you get to the visible part of the spectrum that chemical reactions can be initiated by a single photon. And that's why we can see photons of light hit the retina in the back of our eye and have enough energy to initiate a chemical reaction. That chemical reaction stimulates the nerves and allows us to see. However, once we get beyond the visible light, which can create these low energy photochemical reactions, and we get to ultraviolet light, the energy per photon becomes dangerous. Ultraviolet light not only has enough energy to initiate individual reactions per photon, it also has enough energy to actually break atomic and molecular bonds. So ultraviolet light is dangerous to us. It can give us sunburns, but it can also create cancer. Although it doesn't penetrate much beneath our skin, it's not a very penetrating radiation, it does cause skin cancer. To the next part of the spectrum, we get to the X-rays. X-rays have even more energy per photon. They're even more dangerous because they can penetrate through the body, and that's why we use them in medical imaging. Not because they're dangerous. The doses that you actually get in the medical image, medical X-ray, are very, very low and pretty much harmless. But because the X-rays can pass through the body, at low doses, they're very good for making images. At higher doses, like ultraviolet light, they can cause cancer and be very dangerous. Of course, gamma rays have the shortest wavelength of all, the highest frequency, the highest energy per photon, and thus they pose the greatest danger per photon for us. They can pass very easily through most shielding material, and again, with so much energy per photon, they can be very damaging to our body. Let's go back to the radio waves. The radio part of the spectrum is commonly used, as a means of communication. We've used it for well over 100 years to communicate over large distances. Now, the government in the United States actually divides the spectrum according to its frequency and assigns different frequencies to different applications. It's also categorized according to the frequency, usually in powers of 10. The lowest wavelengths, called VLF, very low frequencies, are so low in frequency that they really don't carry very much information. The interesting thing about them is that they actually penetrate very deeply into the ocean. So the military does use very low frequencies to communicate with submarines, but they can't send very much information doing that once the submarine is submerged. Lower frequencies, same thing. Actually, LF and MF, low frequency and middle frequency waves, are used in, generally part of the radio spectrum that people don't pay much attention to anymore, and that's amplitude modulation, or AM radio. High frequency and very high frequency, HF and VHF, are used, mainly for things like, private communication is where HF is used. VHF was originally used to broadcast televisions, but now is primarily just used for FM radio. Most television is now broadcast in UHF because it can carry more information. And up in the UHF, or ultra-high frequency part of the spectrum, we have things like cell phones that communicate. We have things like cordless phones that use these frequencies to communicate. And of course, broadcast television channels, which are not as popular as they used to be, with cable and satellite, are up in this range. And also, satellite television is actually broadcast in this range. Then you start getting into the microwave parts of the spectrum. Super high frequency and extremely high frequency are really more part of the microwave part of the spectrum than the radio part. In astronomy, radio waves are important because radio waves tend to penetrate obscuring material. Much of our galaxy center is obscured by dust and gas, which absorbs visible light, but radio waves actually pass through a lot of this. And radio waves are also emitted by hot plasmas. Here's an actual picture of a galaxy, and we can see the visible light in white. It doesn't look very impressive. It just looks like sort of a fuzzy blob. But beyond that, we can actually see two huge radio lobes surrounding this galaxy, and these are the result of a black hole at the center of the galaxy. As this black hole consumes matter, as matter falls into the center of the black hole, it converts about 10% of that matter into pure energy. And this energy creates these high energy plasma jets, which have been pouring out into space for a very long time, producing these large radio lobes. So, one of the applications in radio astronomy is actually to try to image regions of low density but very hot plasma. And active galaxies are a very good source of this material. So it tells us a lot about what is happening inside the center of the galaxy. Microwaves are found in many devices. You, of course, can guess that a microwave oven uses microwaves to heat water, any food with moisture in it. The microwaves will cause the water molecules to spin faster, and that actually causes them to heat up. Microwaves are both absorbed by water. That's why they can be used as a microwave oven, but they're also scattered by water molecules. And that makes them ideal for the use in weather radar. So we can actually image the falling rain using a beam of microwaves and seeing how the microwaves are scattered off the falling raindrops or following frozen precipitation, whatever is present in the atmosphere. In astronomy, microwaves also have an application. Generally, microwaves are emitted by some of the coldest materials in space. And the cosmic background radiation, really the energy or echo left over from the Big Bang, the beginning of our universe, glows now in the microwave part of the spectrum. When our universe was very hot, it was glowing well into the gamma ray part of the spectrum. But as our universe has expanded over the last 13.7 billion years, it's cooled, and now it's only a few degrees above absolute zero. So it now glows in the microwave part of the spectrum, and we use satellites such as WMAP to try to image some of this cosmic background radiation. Infrared light, sometimes people call it heat light. The reason for that is that when infrared light shines on the surface of materials, it's easily absorbed. When it shines on the surface of our skin, we feel warm. But infrared light not only is easily absorbed by our bodies, we actually emit infrared light because we are, approximately the temperature at which 10 micron infrared light tends to glow. Here's an interesting set of pictures. You can see a person's hand and actually the handprint from putting their hand on a table. Both are glowing in the infrared because, again, they're warmer than the surroundings. This picture right here is actually a set of different glasses with different temperature water. This glass right here is ice water, and therefore it gives off very little infrared light. This glass is at room temperature, so it glows just about as much as the rest of the room. Then you have progressively lukewarm, warm, and boiling hot water. And in this colorized image, white shows the largest amount of infrared emissions. Now, infrared light is also used in communication. We call this near infrared because it's near the visible part of the spectrum. Most people think that visible light is used in fiber optics. That's usually not the case. Most of the communication that's done with long-distance fiber optics is done in the infrared part of the spectrum because the glass that is used in these fibers actually is more transparent to the near infrared than it is to the visible light. So there's another application. But we're interested in what we use infrared light for in astronomy. Infrared light is nice. It's more penetrating than visible light. It can see through particles. It can see through smog. And it also shows us regions which are warm, not necessarily as hot as stars. Stars glow in the visible part of the spectrum, but regions that are warm where new stars might be forming. Now, in this image shown on top right here, we see the Whirlpool galaxy, and what is being shown here is not so much the individual stars, but actually the star-forming regions, which glow, pretty brightly in the infrared part of the spectrum. And again, you can see where the stars or new stars are coming to life, and again, they're primarily located in the bands of the spiral galaxy. This other image down here shows a planetary application of infrared light. Here you see the very interesting moon of Saturn, known as Titan. Titan is the second largest moon in the solar system, second only to Ganymede, which is a moon surrounding Jupiter. And Titan is very unique in that it has an atmosphere that's actually denser than the atmosphere on the Earth. And therefore, it makes it very difficult to see Titan's surface in the visible part of the spectrum. Titan, being so far away from the sun, receives very little energy or heat from the sun, and it's basically so cold that natural gas, which is primarily methane, would be in liquid form on the surface. The high amount of methane in the atmosphere actually creates a smog or a haze that in visible light just makes it look like a big orange ball. But as you can see in this image, in the infrared light can actually penetrate the smog or this haze, allow us to see some very important surface features. Of course, visible light is the most familiar part of the electromagnetic spectrum. It's the only part that we can sense directly. I know we can sense infrared light indirectly from the heat that it provides when it shines on our skin. It makes the skin feel warm. But with visible light, we can really have a direct sense of it because we can focus it onto our retina using our eye. And it's also the most intense part of the spectrum from the sun. So it's no surprise that human beings have adapted to have their vision primarily in the visible part of the spectrum. The visible part of the spectrum, like the total electromagnetic spectrum, is broken into different parts. Of course, we know these as colors. There are 6 different colors. Red, which actually spans the largest range of frequencies, is also the longest wavelength. Orange is a very narrow band of frequencies. Yellow even narrower than that. Green light is the light that we're most sensitive to. Our eye actually detects green light the easiest of all the light. Blue, a little bit shorter than that, and on the far end, we have violet. Notice that on each side we're surrounded by parts of the spectrum that we can't see. Infrared light at longer wavelengths, ultraviolet light at higher frequencies. Again, in astronomy, the primary source of visible light are stars. Stars' surface temperatures can range from 3,000 degrees Kelvin, where they glow mainly in the red part of the visible spectrum. They actually give off more infrared light than they give off visible. And then up to 40,000 degrees Kelvin, where they glow mainly at the violet end of the spectrum and actually give off more ultraviolet light. But again, for the average star temperature, the most intense peak that they give off will be in the visible. So, when studying stars, visible light has always been a very good way to do that. The sun, having a surface temperature effectively of about 5,600 degrees Kelvin, again makes the peak intensity somewhere around the yellow part of the spectrum. Again, cooler stars tend to be redder, hotter stars tend to peak in the blue part of the spectrum. Now, ultraviolet light is light that's just slightly shorter in frequency than violet light. Your eye can't detect ultraviolet light under normal circumstances because both your cornea and the lens of the eye actually absorb it. If you have cataract surgery where the lens of the eye becomes opaque and then is removed, you can actually see some near ultraviolet light because the lens absorbs so much of this light, preventing you from normally seeing it. But ultraviolet light is very dangerous to the eye. By observing the sun, Galileo actually ended up blinding himself, giving himself cataracts due to his exposure to ultraviolet light. Ultraviolet light is also the primary source of skin cancer. And meteorologists have been very concerned with concentrations of ozone because that protects the Earth's surface from ultraviolet light. Ultraviolet light is a very ionizing radiation and would kill plant life on Earth without this ozone protection. Again, we've been very concerned about the ozone layer because it was depleted by chlorofluorocarbons, which were in aerosol cans many, many years ago. In astronomy, ultraviolet light is mainly emitted by objects that are between 10,000 degrees and 1,000,000 degrees. And here we can see the sun's corona, which glows very brightly in the ultraviolet. And you notice that the surface of the sun doesn't glow very strongly at all. Young blue stars are one of the largest sources of UV light in our galaxy. X-ray, now we're to the second shortest, the second highest frequency of the electromagnetic waves in the electromagnetic spectrum. And again, X-rays are made of very high energy photons, easily penetrate through most matter, so they're very nice for creating images. These are actually CT images or CAT scan images in the human body. And the way that the CAT scan works is that it produces a beam of X-rays that's scanned across the body to create these slices, virtual slices. X-rays are produced by taking electrons, accelerating them to high energies, and then colliding them with a metal target such as tungsten. And this is how the X-ray tube produces X-rays. In astronomy, X-rays are very useful for finding some of the hottest phenomena that are in our universe. Here we see solar flares. These are very small flares, giving off ultraviolet light on the corona of the sun. Flares are sudden bursts or releases of energy when the magnetic field of the sun breaks. They're also emitted by things like pulsars and neutron stars. These are remnants of dead stars. Supernova remnants themselves give off X-rays, and even black holes give off X-rays. So X-rays are very important for studying some of the hottest phenomena in our universe. Gamma rays are even higher in energy than X-rays. They're even more penetrating than X-rays. Now, normally they're given off by radioactive nuclei, and of course, one of the dangers of radioactive material, is the gamma ray. Here's a picture of Chernobyl, which is the nuclear power plant in the Ukraine, which had a massive meltdown. After it melted down, it deposited or it emitted a tremendous amount of radioactive material in the surrounding countryside, and really made a very large area unlivable to this day. Gamma rays are also seen in astronomy in some of the most violent events that we know of. There are only a few events that get hot enough to actually produce gamma rays. One of these events is the supernova, death of a massive star. Will not only give off a lot of bright light, a lot of X-rays, it also emits quite a bit of gamma ray radiation. Magnetars are highly magnetized neutron stars. Neutron stars have a very intense magnetic field to begin with. And these special neutron stars will actually deform their crusts as the magnetic field rearranges itself, producing a large burst of gamma rays. Finally, gamma ray bursts are some of the most intense phenomena that we know of. We can have the merger of two neutron stars producing a massive burst of gamma rays, or we can also have the destruction of a very massive star, which will release gamma rays. In all of these cases, you're talking about tremendously high temperatures. Temperatures that, again, can be in the billions of degrees Kelvin, even the trillions of degrees Kelvin. At these temperatures, this is when you release a tremendous amount of energy in these high-frequency electromagnetic waves. So those are the 7 parts of the electromagnetic spectrum. The problem with using this information to study the universe around us is that not all of this radiation will actually make it to space, make it through our atmosphere. A lot of it is actually absorbed by the atmosphere, and this is good, especially with the ionizing radiation, which is completely, not entirely absorbed, but absorbed at all wavelengths to some degree, and that protects life on Earth. Once again, ultraviolet light, X-rays, gamma rays, these are all types of ionizing radiation which can do damage to living beings. And again, if any of this radiation came to the surface of the Earth in large quantities, life on Earth could not exist on land because there would be nothing to protect or shield these organisms. In fact, land life on Earth was not believed to begin until there's enough ozone to absorb ultraviolet light. Other parts of the spectrum, such as microwaves and radio waves, tend to be absorbed at different degrees too. Now, here's a very interesting chart. It shows the different parts of the electromagnetic spectrum and what parts make it through and what parts don't. And very little of the spectrum actually makes it to the surface of the Earth. Now, again, gamma rays, X-rays, ultraviolet light. All these three parts, the electromagnetic spectrum, are pretty much blocked by the atmosphere. UV basically is blocked by the ozone layer. X-rays and gamma rays are blocked just by the general atmosphere itself. They don't make it very easily into the atmosphere. We do see that a small window, known as the optical window, opens up for visible light. So all parts of the visible part of the spectrum do make it through. But again, the infrared part of the spectrum is pretty much mostly blocked, mostly by water vapor in the atmosphere. Same is true with microwaves. They're primarily blocked. And most radio waves are blocked, but there is a small window where some radio waves can make it through. So if you're sitting on the surface of the Earth, you really don't have many options in terms of looking at the electromagnetic spectrum. It's pretty much, you can look at the visible part of the spectrum, or you can look at a small part of the radio spectrum, but other than that, all the other parts are pretty much blocked from the surface. So let's start with telescopes. There are basically two types of telescopes, optical telescopes and radio telescopes, which we use on the surface of the Earth. And again, that's because that's the only type of electromagnetic radiation that can make it to the surface. Before telescopes, of course, the human eye was the only instrument that we had to observe. Tycho Brahe, of course, had the quadrant to help measure angles, but he used these quadrants with his eye, so the eye was basically the only optical element of that device. Now, if we look at the eye, it has a few different optical elements. The cornea is actually the main focusing part of our eye. It causes the light to converge so it can focus on the retina. The lens of the eye does some of the fine focusing. It allows us to accommodate between near vision and far vision. And then finally, back here, the retina actually senses the radiation, the light. The eye is great for what we use it for just observing around us. But because most objects in the sky are so distant, our eye has very limited in providing any detail, to these objects. So Galileo took a device which was used primarily as a military tool. The telescope was not invented by Galileo. However, Galileo adapted the telescope to his own uses and actually created some of the best telescopes of his time. Before this, these spy glasses were used primarily in the field of battle or on ships, and were really in their infancy, and certainly creating lenses with good optical quality was not possible at that time. So Galileo, of course, creates a very high quality refractor telescope, meaning that the front lens, the lens, that the optical element that the light first is focused with, the objective, is a lens. And this refractor telescope allowed him to make some very important observations to support the heliocentric model of the solar system. Now, what is important with regard to the telescope is, of course, the quality of the images that it produces. If you have inferior lenses and mirrors in a telescope, the image quality is going to suffer. But even with the most perfect optical elements in a telescope, the telescope does have limitations. Telescopes can magnify an object, but only to a limit. And this limit, known as the resolution, depends on the size of the objective. So the larger the telescope, generally, the larger the image that you can magnify, or I should say, the greater the magnification you can make before the image quality suffers. The other thing that's important is the wavelength of light that you're using um, is inversely proportional to the resolution, which means the smaller the wavelength that you use, the better the image is going to be. So, basically, if you're able to focus, shorter wavelengths, higher frequencies, for the same telescope, you can generally get a better image. Now, with an image, and when we're looking at the sky, we're looking at these different objects, we're not only trying to magnify them, we're also trying to see more detail, especially in dimmer or more subtle objects. So bigger telescopes also gather more light, making it easier to see what we're viewing. So larger telescopes are superior to small ones because they have better resolution, but they also have better light gathering power. Now, Galileo's telescope was not all that great by today's standards. Certainly it was superior to anything that anybody else had produced. But his telescope, like all refractor telescopes, suffer from two problems. One is the way that they grind the lenses, or they shape the lenses. The lenses are shaped with spherical surfaces. Really, the surface should be a different type of shape. It should be parabolic or hyperbolic. But the way that they're ground, mechanically, it's almost impossible to grind them into any other shape but a spherical shape without spending a lot of money. So Galileo's telescope suffered from spherical aberration, which causes the light to focus at different points due to the spherical nature of the lens. It also suffered from chromatic aberration. And this is due to the fact that blue light is refracted more strongly than red light. And, chromatic aberration basically makes a lens behave like a prism. So, Galileo's images were, suffered. Of course, he had no film back then to take images, so we can only reproduce his telescope and imagine what he saw. But, the images did suffer due to this chromatic aberration, spherical aberration. Today's telescopes, which are refractors, actually use multiple lenses to get rid of some of this aberration. And this is what's known as the achromat, which is a two-lens combination, which actually focuses the light a lot better without as much chromatic aberration. Even more complex systems like apomats use three lenses rather than two to improve on the chromatic aberration even more. Spherical aberration, as you can see, causes the light to focus at different points depending on where it enters the lens. And again, this is because the lens shape is not ideal. Again, multiple lenses can be used to get rid of some of the spherical aberration, but Galileo at his time only used a single lens. Both the, primarily the chromatic aberration was a problem for Sir Isaac Newton. And Newton, coming after Galileo, actually decided to make an improvement over Galileo's invention. Well, it wasn't really Galileo's invention. And instead of using a lens for the objective, the refractor telescope, he was able to use a curved surface or a curved mirror to create the first reflector telescope. And this is a huge improvement over the refractor because it suffered from less aberration, but it also was easier to make. Now, with a lens, you have to polish each surface, and that's very time-consuming. With a mirror, you only have to polish one surface, the surface that's reflecting. So a reflector telescope takes much, much less work to produce a mirror of equal size to a lens, and therefore generally reflector telescopes are more efficient cost-wise. The modern reflector telescope still uses the invention that Newton gave us. And here we see a special type of telescope. This is actually one of the Keck telescopes, a very large telescope in the Mauna Kea in Hawaii. It's one of the largest telescopes in the world. And it actually uses many mirrors arranged in sort of like a mosaic sort of like a tile. And again, the advantage here is you don't have to have a large lens which is ground on both sides. You just polish one surface as opposed to many surfaces, and this really saves on cost. Again, here's another view of the Keck telescopes. This from up above. They're actually a pair of telescopes, and these telescopes each have a huge diameter of 10 meters across, which means they have a tremendous amount of light gathering ability, but they're also very high in resolution. The reason why they put these two telescopes together is that using a special technique called interferometry, they can boost the resolution even higher by using the two telescopes and combining the images at the same time. It's a very difficult process because everything has to be done very precisely. But this interferometry gives the two telescopes working together an equivalent resolution equal to 100 meters as opposed to the 10 meters that they actually are. So visible light makes it to the surface of the Earth. And generally, the optical telescopes that we have use either lenses, refractor telescopes, or mirrors, reflector telescopes, to focus this light and allow us to see at higher magnifications and see dim images much brighter because it can gather more light. The other part of the spectrum that does make it down to the Earth is the radio part, and that led astronomers in the 1950s to start trying to reproduce the telescope, but make telescopes that worked in the radio part of the spectrum. The nice thing about the radio telescopes is they're not very demanding in terms of the reflective surfaces. With an optical telescope, you have to polish that surface down to 1/10 of a wavelength. That's basically make it smoother than a 1/10 of a millionth of a meter. You can't have any imperfections greater than that. The radio telescopes, you basically just have to create a fairly, smooth, no big bumps, no bumps bigger than, maybe a centimeter, metallic reflector. It can just be made out of thin sheet metal, and this essentially focuses the radio waves to a detector. Now the problem is, due to the long wavelength of the radio waves, the resolution of the radio waves, radio telescopes is really quite poor. Again, optical wavelengths are in the hundreds of nanometers, or roughly about 10 to the -5 meters, whereas radio waves would be in the centimeter or even meter range. So there can be anywhere from a factor of 3 to 5, magnitude of 3 to 5, difference in the resolution, which means that you need a radio telescope 1,000 times bigger than an optical telescope to get the same resolution, or even 100,000 times bigger. Now, however, despite, I should say, this resolution problem with radio telescopes, they can use interferometry much easier with radio telescopes and create an equivalent or a giant single telescope like what is seen down here. Here's a single radio telescope, but here's the VLA array in New Mexico, which combines all the information from many telescopes to have an equivalent diameter of a few kilometers across. So again, radio telescopes, just looking at a different part of the electromagnetic spectrum. One of the problems with visible light as it passes through the Earth's atmosphere is, we saw with the chapter on the night sky that visible light is somewhat scattered and is somewhat refracted by the atmosphere as it makes its way to the surface. The scattering creates light pollution, which can degrade the images for these telescopes. But even worse, the atmosphere is constantly moving, which can create refractive problems, which would blur the image. We call the quality of the sky seeing. And the further you are in altitude, the further up you are in altitude, the less the atmosphere can disrupt the light coming in. That's why most observatories are on tall mountain peaks. Mauna Kea in Hawaii, in Chile, they're up in the Andes Mountains, these very large observatories. But the problem is you can't get above all the atmosphere. The mountains don't exist at such high altitude that they go off into space. So eventually, astronomers decided that the only way that you can get around this atmospheric disturbance completely is to put the telescopes in space. Now, we've gotten a little bit better with handling atmospheric turbulence by using fast computers and special actuators that will actually deform the mirror to match the turbulence in space. But again, nothing beats putting the telescope up in orbit, and that's where the Hubble Space Telescope comes. The Hubble Space Telescope is not a large telescope by the standards that we have for Hawaii and Chile. In both these locations, we have telescopes that are over 10 meters across in diameter, the mirrors, while the Hubble Space Telescope only has a mirror diameter of 1.2 meters. But again, very few telescopes can even approach the resolution limit of Hubble, because Hubble doesn't have to deal with the atmospheric turbulence. Hubble can fail at any time now, and NASA has canceled any future repair missions because the space shuttle has been retired. So, hopefully we'll have Hubble around for quite some time. But we're already building Hubble's replacement. This is known as the Webb Space Telescope. And originally it was supposed to be launched by now, but NASA cutbacks and engineering delays have pushed the telescope back to probably no sooner than 2020. So hopefully Hubble will remain in operation until the larger Webb telescope can be placed in orbit. The Webb telescope will not be an equivalent replacement for Hubble. The Webb telescope actually looks in the near infrared rather than the visible light, so it looks at slightly different wavelengths than the Hubble was designed to see. But putting observatories up into space has been very costly, but it also has led to a lot of discoveries that we just can't see on the surface. Other space telescopes that are in operation or planned are up there that look at all parts of the spectrum. For instance, the Spitzer Space Telescope is a large space telescope, not quite as big as Hubble, but this has provided us with spectacular views of objects in the infrared part of the spectrum. On the other side of the spectrum, the Chandra Space Telescope allows us to look at the X-ray wavelengths. And, with the use of Hubble, which can see visible, some near infrared, some near ultraviolet, Spitzer, which can see into the infrared, and Chandra, which can see into the X-ray part, we've really covered a very large part of the spectrum. Here's another interesting observatory, SWIFT, which is basically a telescope that looks at many different wavelengths, but is designed to study gamma ray bursts. This telescope waits for a gamma ray flash, turns its small telescope in the direction of where that flash came from, and then tries to observe ultraviolet light and visible light from the gamma ray bursts after the initial explosion. SWIFT has actually been replaced by Fermi, and Fermi is a much more sophisticated gamma ray telescope that allows us to actually get pretty good resolution of distant gamma ray sources. The Wilkinson microwave anisotropy probe, also known as WMAP, studies primarily microwaves, and it's allowed us to observe microwave radiation from the Big Bang. We know it as a cosmic background radiation in very good resolution and detail. Here's another space probe, SOHO. One of the big problems with studying the sun was we discovered that by watching the surface of the sun rise and fall, we can actually see seismic waves within the sun. And like seismic waves allow us to see within the Earth's center, these seismic waves have told us a lot about what's inside the sun. The problem is some of these seismic waves have such low frequencies that they take days to oscillate. And on the Earth, because the Earth rotates, we can only watch the sun for a limited amount of time before it would set. So SOHO can watch the sun at all times and give us very vital information about the sun's interior, allow us to understand the core where nuclear reactions actually take place. So those are some of the observatories that we have orbiting the Earth. And again, the idea is the atmosphere does protect us from a lot of dangerous radiation, but it also inhibits us from seeing some of this radiation and using the information from this radiation to investigate the universe around us. Although it's costly, it's been very rewarding to put these observatories in space, and they've really created a revolution in astronomy with all the information that they've given us. Now, the other option besides simply observing is to actually travel to a location. But again, we're limited. The best we've done is send humans to the moon. Robotically, however, we've been able to send space probes pretty much all over the solar system to get a better idea of what's out there. So, human beings, getting them anywhere off the Earth is very costly because human beings need a life support system. And again, the best that we've been able to do is put people on the moon. And it's been since the 1970s that anybody's walked on the moon, and there's a very good reason for that. It's so expensive to put people there, and it can be done much more easily by sending robots which don't need life support. In terms of investigating the solar system, there's a limit of where we can send space probes because the nearest star would take hundreds of years to get to, even with the best technology that we have today. And of course, it's not even sending a person there, that's sending a space probe, and getting the signal back from the space probe would take a very long time. So for now, space probes are good for investigating the rest of the solar system, but not much beyond. Usually space probes come in a few different types. You usually have flyby missions, orbiters which simply take pictures and make measurements as they pass by, or go into orbit around the planet. And the most sophisticated are the landers, which may include things like mobile rovers like we have on Mars. In terms of Mercury, we've initially only sent one space probe past Mercury, and that was Mariner 10. However, recently we've actually placed a satellite in orbit around Mercury, and it's currently giving us a lot of information about this planet. Mercury is a planet very close to the Sun. Its low mass and high temperature cause it to not have an atmosphere. But the space probe Messenger did arrive at Mercury, is in orbit, and is currently taking some very spectacular pictures. Venus, we've sent a lot of missions to Venus, both the former Soviet Union, Europe, and ourselves. We've been able to study this planet pretty extensively, even though it has a thick atmosphere and a dense cloud deck that prevents us from seeing the surface from space. The Soviet Union sent quite a few landers on the surface. Here you can see a color image of some of the rocks on the surface. They're a volcanic rock that we call basalt. But one of the most successful missions to Mercury was actually Magellan, which used radar to map the surface and gave us not true images of the surface, but allowed us to see the surface topographically and create computer projections of what the surface might look like. Mars has been very extensively investigated. Initially, space probes such as Viking 1 and 2 landed on the surface. These were landers that weren't able to go. I don't think we'll ever send a human being in real time, but anytime soon. But following the Viking missions, we've been able to send a very small rover, Sojourner, and then we followed that up with Spirit and Opportunity, and most recently we've sent Curiosity, which is the largest of the rovers. Well, Spirit and Opportunity were probably about the size of a large desk, if you will, or a large table. Curiosity, which has just landed on Mars, is about the size of an SUV. To Jupiter, we've sent both Voyager 1 and 2, and I apologize for this slide. We also sent the Galileo space probe, which we see down here, and that's given us quite a bit of information about the planet, but also its moons. To Saturn, we sent both Voyager 1 and 2, and we also sent the Cassini space probe, and that's currently in orbit and studying Saturn at this time. Uranus and Neptune really haven't been investigated very much. Voyager 2 did go out to them, but they only received flyby passes. So they're probably the two planets that we know the least about because they've been studied the least. Pluto will soon have a flyby mission past Pluto. New Horizon was launched. It is on its way. It will arrive at Pluto probably, I believe it's scheduled to arrive about 2015. So in a few years, we'll have our first images of Pluto. And right about the same time, another space probe will be arriving at Ceres. So we'll see two dwarf planets for the first time nearly at the same time. The Dawn mission is the one heading towards Ceres. It just left the asteroid Vesta. Again, New Horizons is going toward Pluto. Now let's talk about the last thing. A very important tool in astronomy, the spectrograph. It produces spectra from light or any type of radiation by breaking it into its individual frequencies. The simplest type of spectrograph is just a simple prism where we send the light through and break it into its individual colors. The problem with this is the prism spectrograph is made out of glass, and glass absorbs light in the infrared and ultraviolet part of the spectrum. So it's really only good for visible light. Diffraction gratings, however, have a much larger wavelength range, I should say frequency range, at which they can be used. It's the same effect that you see with CDs and DVDs. You shine light on them and it breaks it into its different colors. And this is due to this closely spaced lines on it. And the same thing is done with the diffraction grating spectrometer. We use this grating to create an interference of the waves, which sends the violet light at one angle, the red light at another angle, and that allows us to break things into its different colors. This can be done at any wavelength. We have spectrometers that go all the way to the X-ray part of the spectrum that use crystals to diffract the light. It works at the ultraviolet part of the spectrum using diffraction gratings. The same technique works for visible light, infrared light. For microwaves, we can actually use some type of an electronic tuner, as well as a radio tuner to determine the different frequencies and wavelengths. And for gamma rays, we actually use particle detectors to determine the spectra. So, again, very important tool, probably underrated in terms of its importance in astronomy, is a spectrometer, which again breaks any type of radiation into its individual energies or frequencies. So in summary, the electromagnetic spectrum consists of 7 parts: radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma ray. The visible part of the spectrum, 6 colors. Telescopes with lenses as their objectives are known as refractors. Telescopes with mirrors are known as reflectors. Because visible light and radio waves are the only ones that can make it to the surface of the Earth, originally we only had optical telescopes, refractor and reflectors, and radio telescopes. Now we can place telescopes in orbit, and we can see any part of the electromagnetic spectrum because of this. Even in the visible part of the spectrum, space observatories such as Hubble are far superior to what we have on the surface of the Earth. And finally, space probes allow us to look at planets close up. We visited all 8 planets, and spectrographs or spectrometers break electromagnetic radiation into its individual frequency components, which allow us to measure important things such as, once again, temperature, composition, and even speed. Okay, that's it for today's presentation. I'll put it in the archive and see you for the next one, Chapter 5, Formation of the Planets.